Hey guys, in today's video we're going to continue our journey of seeing if I can persuade you that right now you don't exist, and today we're going to do it by looking at quantum mechanics. So yeah, wish us luck. Any video I've seen on quantum mechanics always starts with this quote from Richard Clayderman, where he says, "The piano, by its black and white keys, first attracted me. My father showed me how to use, and slowly I got into playing." You sure about that, mate? It doesn't sound very quantum. Oh, the quote should be by Richard Feynman. Well, that makes more sense. The quote by Richard Feynman says, "Anybody that says they understands quantum mechanics doesn't understand quantum mechanics." That's not exactly true, because my little friend over here assures me that he's broken the laws of quantum mechanics and we've discovered time travel. So rather than just bringing you quotes like this one, we're going to go back in time and actually interview the main players of the time. So yeah, I'm ready when you are. Let's go! Oh gosh, I feel terrible. It hasn't worked. What's gone wrong? Oh, you forgot to charge the battery? I thought you said you had all of this. Oh, right. Anybody that says they understands quantum mechanics doesn't understand quantum mechanics. I f***ing hate you. You're watching Icing. When Feynman made this quote, it was a little bit tongue-in-cheek, because we do understand quantum mechanics and quantum theory. You wouldn't be able to watch this video if we didn't. Quantum mechanics has managed to produce the standard model, which is one of the most accurate models we have in all science. The accuracy that comes from the predictions of this model are staggering. Feynman himself shared the Nobel Prize in 1965 for his work on quantum electrodynamics, which was joining the quantum mechanics and the theories of quantum mechanics with Einstein's special relativity. Feynman's work on QED has set the template for all future work on quantum field theory. So when he says people don't understand quantum mechanics, there wasn't many people on the planet with a better understanding of quantum mechanics than Feynman. What he meant by this quote, bearing in mind Feynman was a mathematician, was through the construct of mass, able to describe and accurately predict what was happening in the quantum world. But to use the scientific term of what it was describing, it's batshit crazy. Being able to describe it mathematically is all well and good, but actually understanding what is going on down there, nobody's really sure. Some of us have probably been out of school for a while. So how am I going to be able to use quantum mechanics to try and persuade you that right now you don't exist? Bearing in mind, the vast majority of you are going to be sitting there going, I've got pretty good evidence, mate. So let's just have a very quick recap about atoms and matter. So those of us that are going, I'm here, mate, we can look at what the actual atomic structure is. We've got an animation to do this. We're going up in the world. Yeah, okay, roll it. No, fantastic. Whoa. Seriously, mate. What the f*** is that? We've spent all the budget. What have we spent the budget on? Oh, of course, the time machine. Remind me again, what does a time machine run on? Cigarettes and Guinness. And vodka. I'll just roll it, just get on with it. The fundamental feature of the electron is it is negative. As in, it is negatively charged. It also has virtually zero mass. The centre of the atom contains the protons and the neutrons. You can do this. You can do this. And these are positively charged and neutral charged, but they both have mass. You can do this. You can do this. Both the proton and the neutron can break down further again into quarks, of which there's two types. The up quark, which is positively charged, and the down quark, which is negatively charged. In the proton, you have two up quarks and one down quark, and in the neutron, you have two down quarks to one up quark. And when we take the sum of the charges, the 2 up quarks to the 1 down quark makes the proton positive, and the 2 down quarks to the 1 up quark in the neutron balance out to give us a neutral charge. So it's the nucleus of the atom that gives it its mass, and then there's a cloud of electrons that orbit around to produce all of the atom. Now, as you will see, most of atoms contain nothing at all. It is noted that if the nucleus of an atom was the size of a grain of rice, you could place it in the centre circle of a football field, and the electrons would be orbiting around in the stadium, and in between the electrons and the nucleus is nothing at all. Atoms is basically space. I have absolutely no words to describe the atrocity that I've just witnessed, so thank you for that. So quantum mechanics sometimes gets described as God's Lego set, because there's 4 fundamental particles that we know about that can't get broken down any further. We saw 3 of them in the video, which is the electron, the up quark and the down quark. And there's also a 4th one, which is the neutrino, but because neutrinos don't really interact with matter that regularly, we're just going to ignore them for the simplicity of this video, if that's okay with you guys. To give us an idea of how small subatomic particles actually are, think of a grain of sand. Now, contained within 1 grain of sand are more subatomic particles than there are grain of sand on Earth, allegedly. Quantum mechanics really had its golden age in the 1920s and 1930s, where there was lots of fantastic scientific thinkers all working on the problems which came out of quantum mechanics, each one bringing their own solution to the puzzle which was in front of them. This image is sometimes referred as the photo with the highest IQ, because 10 of the individuals in this photo went on to win the Nobel Prize in Science. Those of you with your eagle eyes will notice there's only 1 woman in this picture, but she's also the only person that won 2 Nobel Prizes in different fields of science, 1 in physics and 1 in chemistry, and that's Mary Curie. But for our story today, let's just focus on the key individuals, starting with the one that we probably all recognise. Silly one stone. Albert Einstein. You sure about that, mate? I've looked it up, I translated it. It's like, oh, okay. Alright, Albert Einstein. This photo was taken in 1927 at the Solvay conference, and by this time Albert Einstein was at the height of his power. His general theory of relativity had been published for about a decade, and a lot of the predictions that it was making had been borne out by scientific experimentation. Most notably was the experiment conducted during a solar eclipse which proved that mass warps space-time so that light will bend round objects, and in this case it was the solar eclipse that blocked the sun, and a star that should have been hidden by the sun, its light was visible, proving that light had curved. This made Einstein a household name, and he was also going to be one of the key players in quantum mechanics, more so for how outspoken he was against what quantum mechanics was predicting. If we shift our attention across here to the left, here's a gentleman called Max Planck. Now, Max Planck says his greatest discovery was Albert Einstein. Pretty much true, because in 1905, when Albert Einstein wrote 4 of the greatest scientific papers of the time, they could have gone unnoticed. But fortunately, somebody put one of these papers on the desk of Max Planck, and he was clever enough to realise the genius of Albert Einstein's work. So this goes to show it's so important that you share other people's work amongst your friends and colleagues and get the word out, because out there's undiscovered geniuses. Not really a plug, but if you want to share this video with people, you know, just saying. There's a bit of an argument to say, if it wasn't for Max Planck, would we have known about Einstein's theory of relativity, or would it have just got lost and never discovered? Max Planck was an amazing physicist in his own right. He had started to work out what many of the universal constants are and started to put his name to them. So you could say he was constantly naming constants. Yeah, he does sound like a total constant. Oh, that's not what you said. One of the constants I need to bring your attention to is something called the Planck length. Now, the Planck length is the smallest measurement in length that we can make. There's no point having a half Planck length because the Planck length can contain the smallest things that exist. So going smaller has no value. To give you an idea just how small a Planck length is, pluck out a hair. You could have plucked it out your head, mate. Oh, seriously, put it away. If we were to take this hair and zoom in on it and keep zooming in and keep zooming in so the hair gets bigger and bigger and bigger and we keep zooming in and now the hair's the size of the observable universe, a Planck length would still be the width of that hair on top of that hair that's the size of the known universe. So if we start to shrink this hair down and the Planck length is shrinking with it, that when we get this hair down to the size of, well, a hair, just imagine how small that Planck length must be. It's so tiny, it's like it doesn't almost exist. Shifting our attention across here to the back row, here we have Erwin Schrödinger. Now, the name Schrödinger may be familiar with you because he had a thing about torturing cats. Now we come across to this chap, Werner Heisenberg. You may be familiar with the name Heisenberg from this TV show, where there was a chemist who took the pseudonym name of a physicist, because that makes sense.
You're goddamn right.
Heisenberg came up with something which is now known as the Heisenberg uncertainty principle, which covers many different facets. The important part of the Heisenberg uncertainty principle is there could be two values which are linked together, and the more you know about one value, the less you can know about the other. So, to use Breaking Bad as the example and why I think they took Heisenberg, when Walter White was being bad, we didn't really know how good he was, and if he was being good, did we really know how bad he was? When you rewatch it, you'll just see he's a bit of a twat.
You're goddamn right.
The part of the uncertainty principle that I want to bring your attention to today is there's two values which are linked together relating to particles. The more you know about a particle's location, the less you can know about its velocity. The more you know about its velocity, the less you can know about its location. And the better you can define one of these two values, the more obscure the other one comes. It would be impossible to be a speed cop in the quantum world. What do you mean you've got footage of speed cops in the quantum world? Shut up. Really? Yeah, prove it. Oh, this is going to be fun.
Whoa! Bah! You stop right there. Have you got any idea how fast you were going? No? Have you? No. Salama. Free to go, yeah. Yeah. Okay. Bah! Wait, we got another one. Where'd you go?
Seriously, dude, where are you getting all this stuff from? Oh, right, yeah. You're connected. And we should be showing them more respect? Yeah, why's that? Because they uphold the quantum law. I'm really glad I asked. They're keeping our reality real, okay? I get ya. Yeah, drunk all our budget by now, have you? Yeah, thought so. And finally, we're going to come over to this chap, Niels Bohr. Now, Niels Bohr was one of the leading figures in the development of quantum theory and quite often came to loggerheads with Albert Einstein. And many of the debates that they had continued across university campuses around the world. One of the key points that Einstein rallied against was the key point of the randomness and the probability which comes into quantum mechanics, and quite famously said, "I don't think God will play dice with the universe," to which Niels Bohr replied, "Stop telling God what to do." Einstein came back with, didn't come back with anything, because my boy ain't no hollaback girl. So let's see if I can start to break down your arguments about particles and how real you must be because we can touch things. If you're unfamiliar with the double slit experiment, you're really in for a treat. We've got an animation of the double slit experiment. Am I going to be embarrassed by this? Oh, I'm going to be surprised, am I? I doubt that. Roll VT. In the double slit experiment, there is an electron gun which will fire electrons singly, one at a time, down a track towards a barrier. Now this barrier is going to have two slits in it, which are a lot closer than the ones that are being demonstrated here. As the electrons come along, they can either go through the slit on the right, the slit on the left, or they could bounce off the barrier. Further down the track, there's going to be a receptor that's going to mark the location where the electrons hit this wall. More electrons will be fired down the track. Because it's firing through two slits, we'd expect the receptor to show they're hitting the wall in two parallel bars. However, what was noticed was a pattern more like this. And this is indicative of an interference pattern. And interference patterns are more noticeable with waves. So if the electrons are being fired singly, how are they managing to produce a wave interference pattern? Yeah, I've just got so many questions, but the main question is, how could it produce an interference pattern if we're firing a little bullet of matter through a gap? What's interfering with it? What is it interfering with? Interference patterns are produced through waves. Now if we imagine we had a wave going through the double slits, and then on the other side of the slits it would interfere with itself. That's so childish. What we would have is, if we've got two wave crests coming together and they meet, they're going to make a larger wave crest. If we've got a wave crest and a dip coming together, when they meet they level out, and if you've got two dips coming together, where they meet they're going to trough out further. So what's happening when it's hitting the sensor at the back and creating this banding? The band in the middle is where most of the crests are going to hit. The dark areas are where the troughs are hitting, and as we get across the wall, most of the crests are going to hit in the middle, and there's going to be less and less hitting towards the edges. The fact that we observed this with the electron must show that the electron was travelling as a wave, went through both slits at the same time, and then on the other side of the barrier interfered with itself. Oh, will you just stop that? What we would need to do is be able to have an observer and find out if the electron is going through both slits at the same time. We've got an observer, have we? Of course we have. How have we managed this? Through your connections. Of course we have. Okay. Now let's try it again.
Hello.
Oh, you are f***ing kidding me.
I'm ready when you
Okay,
are.
hey buddy.
Ah.
No, we're over here.
Okay. I'm
great
ready
start.
when you are.
What we need you to do is count the electrons that are going through the gate on the left. Only the one on the left, okay?
Okay.
Yeah. You can do that, yeah? Okay. See how we get on. Fire the gun.
Rubbish. Okay. There's one. There's one. There's one. There's one.
What you need to do now is go down to the end of the track and count how many bands you can see.
Right you are then. Two. Hang on, let me count them. 1, 2, yeah. 2.
Okay, thank you. So we didn't get any interference pattern. So the electron went through the gate as an electron and stayed as an electron all the way down to the sensor. What we'd really need to do is move our observer the other side of the gate so the electron travels down as a wave and then goes through both slits at the same time as a wave, and we'll see if it interferes with itself. Don't you dare. Right mate. No, we're still over here. Right mate, we need to go the other side of the gate.
You are then.
No, we're still on this side. Oh gosh. Connected, are you? Right.
Hello.
We're going to be firing electrons through that gap, so we want you to get out of the way, yeah? You don't want them going in your eyes. Yeah, don't want them in your eyes. That's like that. Oh gosh. It's going to go blind, isn't he? Right, fire the gun.
There's one. 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 There's one.
Right, go down to the end of the track and count how many bands you can see this time.
I can see 2. Hang on, let me count. 2, yeah, 2.
You sure about that? We were expecting to see an interference pattern of more bands.
Oh, 1 second, let me have a proper look. Yeah, it's still 2, yeah.
Right, okay, that's enough. Thank you very much.
Cheerio.
Yes, bye. Bye now. We're going to have words. As we can see, the results were rather perplexing. What did this mean? When the electrons were being fired and they weren't being observed, they created an interference pattern. Yet when we tried to find out which of the slits it went through, either before the gate or after the gate, the electron acted like a particle and gave us solid bands. Yet unobserved, we get the wave interference pattern. For this explanation, we need to suspend our belief in particles and real stuff. The electron was travelling as a probability wave. It was in all locations at the same time. And it was only when it actually hit the sensor at the end that it had to become real and made its dot on the screen. When it was travelling as the wave and it was observed, using Heisenberg's uncertainty principle, we knew its location, it became real. Which was why it doesn't matter if the observer's before the gate or after the gate, as soon as it's observed, it behaved as a particle. The bit that twisted people's heads though was it travelling as a wave through both slits at the same time, gets observed and then became the particle, or was it a particle all the way through, i.e. the electron knew it was going to be observed, so always behaved as a particle? What if all particles travel as waves until they're observed? And what actual observation needs to take place for this probability wave to collapse to create the hard particle? The largest problem we have with quantum mechanics or quantum theory, and that's the measurement problem. There's two worlds. A mathematically constructed world where everything's in probability in various locations, and the real world of hard objects and items of matter. Which one's actually real? The measurement problem comes about of we don't actually get to see the collapsing wave. Through Heisenberg's uncertainty principle, when we see a particle in its location, it's no longer the wave. What we don't see is the collapsing probability wave that creates the particle. And this is just one of the issues we have of thinking about things as particles, because they're not really real. When we go back and we look at the standard model, and we have our electrons and our up quarks and down quarks, neutrinos, so on and so forth, we're not describing particles, we're describing fields. Now, think of a field as a liquid that permeates all of space. When we go back and think about the Planck length in our three-dimensional construct, if we ignore time, and make the Planck length a Planck cube, and now think that these Planck cubes fill up all of space. Okay, it's how we can pixelate space, so let's call them Planck pixels. What we see are the waves being created in these quantum fields as they move through our three-dimensional construct. In one of our Planck cubes, we will find every single one of these quantum fields, and they can have various different energy levels from, let's keep it simple and say 0 up to 11. So we've got all of these fields, they're not like layered on top of each other, they're all existing inside the same field at the same time, and each one will have different energy levels, so it will have different waves. But the Planck cube next to it will be connected, and the Planck cube next to that, the quantum field will be connected. View it like this. When you look at the ocean, you could have a wave that's hitting the east coast of America, and you can have a wave that's hitting the west coast of Africa. Both of these waves are connected, even though there's thousands of miles distance between the two, because they're all connected to the water. Think of the electron field. Every single electron in the universe is connected through its electron quantum field. Doesn't matter the distance, it's just a ripple occurring within that quantum field. So in that aspect, all the electrons that make up my body are connected to all the electrons that make up your body, that make up all the electrons that make up anything that we can see. In that fashion, everything is one and we're all connected. Yeah, this does really sound like hippie shit. Yeah, it does. Yeah, thanks. What I'm going to try and describe next is the kicker to my argument, and it's whether or not you're going to agree or disagree with my analysis of this. Every individual Planck cube can hold every single value for every quantum field we know exists. Let's call it the Planck pixel. My TV, also made up of pixels, can show me any image pretty much at all. I don't go and buy a brand new TV each time I want to watch a new film. I'll just go and get a different DVD, or even better, I'll just go and stream it these days. My TV is capable of showing me every movie that can be played through it. Now, if we think of the universe being pixelated with Planck pixels, they can show any value of the quantum field. So what's dictating the value in the quantum field, whatever laws are dictating how the fields interact with each other, the universe is capable of showing anything that the quantum fields are able to show, in the same way as my TV would do. Just so happens the universe is currently playing the story of your life. But it's also able to show every other possibility that exists as long as it's made up of quantum fields. Therefore, the fact that it's the story of your life being played is literally 1 in infinity. That's really low odds. The second point we need to look at is the mathematical constructs, or the probability of things existing, far outweigh the real. So again, the odds of this being in existence is 1 in infinity. So the fact you're real is 1 in infinity multiplied by 1 in infinity. So I'm not a mathematician, but that's pretty much close to 0. So the fact that things can exist as a mathematical probability, and all things can exist as a mathematical probability, the chances of it happening is pretty much guaranteed in infinity, at least once. But what if the story of your life hasn't been played yet? We're the DVD still stuck in the box. We have the potential of being shown, we have the potential of being viewed, but it hasn't happened yet. What if everything we're looking at around us is just the probability of its existence? What would a probabilistic consciousness look like? So how have I got on? Have I managed to persuade you that maybe you don't exist? The next episode, we're going to continue this journey of seeing if I can convince you you don't exist. And I'm saving the best for laugh, because it's... Laugh? Saving the best for laugh? Saving the best to last? Because it really is the clincher. If you haven't been persuaded yet, the next one will actually get you. So if this is the type of thing that you really like, hit the subscribe button, because it's going to be so much easier to come back and find this bullshit the next time. But thanks for your time, and if you can f*** off now, because me and him need to have a chat. Thanks a lot.